Hello dear learners, in this video lecture we will learn about another algorithmic technique which is known as backtracking. So what is backtracking? As I told you, this is an algorithmic technique, and here the goal is to get all the possible solutions to a problem using a brute force approach. So we try all the possible solutions which can be there for a particular problem, and here we build the solutions incrementally. Okay, so we have at the initial stage a number of, this is the suppose the initial stage, and we have a number of options, right? So we pick one of these options and then explore it further. Okay, so in this way we incrementally build the solutions, right? And if the problem is satisfying the constraint, because these problems which we will discuss under this backtracking algorithms, they are having some constraints, okay, some foundations are there. So if the solutions, these are the solutions, these nodes, these are the solutions, okay, these leaves. So the solutions that fail to satisfy, they will not be explored further. Okay, so if at this position we found that there is no use of exploring this solution anymore, then we will remove this solution and we will backtrack. Okay, and from here we will explore the next solution. Suppose we also found that this is not feasible, then again we will backtrack. So we will come here again, and again we will explore this solution, and suppose here we found that both of these solutions are not feasible, so we will again backtrack, and from here we will backtrack here, and we will explore the next option, and so on. So incrementally the solutions are built, and if your solutions are not satisfying the constraints of your problem, then you remove those solutions and keep only those solutions which are satisfying the constraints. So this kind of a structure is making a tree, and for exploring this kind of a structure we can use the recursive calling, right? So using the recursive calling we can build the solution step by step, like as we build the solution in a depth first search. Okay, so we pick a node, we explore all its neighbors till the end, and from there we backtrack. So this, all of this can be done recursively, as you know. Okay, so similar kind of situation is arising here. Okay, so we are exploring the solutions incrementally. Okay, so we are picking a branch and we are continuing till we find that whether this solution is a good solution or we find that this solution is not a good solution. Okay, so depending on these two cases we will backtrack. Okay, so this kind of a situation can be best implemented using recursive calling. Okay, so now as I already told you that we create a tree when we are creating the solutions, when we are finding the solutions. Okay, so that kind of a tree which we make in backtracking, it is called state space tree. So it lists all the possible states which a problem can have as the solutions. Okay, so it is representing all the possible states, solutions or non-solutions of the problem, starting from the root as the initial state to leaves as the terminal states. Okay, so you start here, and from here you can see that there are three feasible solutions. Okay, three possible options. Okay, suppose we pick this. Okay, and from this we go further down this branch and we go here, and when we analyze, then we found that this is a good solution. Okay, and from this solution it has no children, so we backtrack. Okay, so we again come here. So we have or found one solution. Now we explore the second option. Okay, uh, we reach this state, and from this state we reach its child this state, and when we analyze, we found that this is not a solution, so we backtrack. We come here again, and from here we found that it has no more children. Okay, it has only one child, which we have already explored. So from here also we will backtrack to the initial state, and at the initial state we explore one more option, that is the third option. So we come here, and from here we go to its children, and it is having one child, and when we analyze this, this is a solution. Okay, so this is how these backtracking problems, they are explored incrementally in the form of a depth first search tree, that is also called state space tree, right? So it uses depth first search method. When it starts exploring the solutions, a bounding function is applied. Bounding function means it checks whether the state which you have reached, that state represents a solution. Okay, so it is a feasible solution if it satisfies the constraints. It is non-solution if it does not satisfy the constraints. So that is the purpose of bounding function. It is applied so that the algorithm can check if so far built solution satisfies the constraints or not. So if it is satisfying the constraints, then we continue searching. Okay, so we will go to its children. If it is not having children, then we will again backtrack, and as we saw in the previous diagram, we explore the next option and so on, right? And if it is a non-solution, if does not satisfy the constraints, then the solution will be eliminated. Okay, so the solution will be eliminated, and we will backtrack and explore the next option. Okay, so this is the general backtracking algorithm. So we are at a node X in this state space. Okay, so this is representing a particular state. So if X is not a solution, then we return false. If it is a solution, that is, if it satisfies the constraints, then we will add it to the list of solutions. And in both the cases, we will, if it is satisfying the solution, then we will expand this. Okay, we will try to explore whether it is having children or not. Okay, and if it does not satisfy the constraints, then we will not explore its children. We will simply backtrack from here. Okay, so this is the general algorithm. Now let us look at an example to understand this backtracking concept more clearly. So for example, you are having a problem in which you have to find all possible ways of arranging 2 boys and 3 girls on 3 benches. Okay, so here this is the problem, and as I told you, the backtracking algorithms also have some constraints which should be satisfied by the solutions. So the constraint here is that girl should not be on the middle bench. Okay, so what are all the possible solutions without any constraints? If we do not consider this constraint, what are the possible solutions? The possible solutions are, there are 3 persons. Okay, so suppose the 3 persons are B1, B2, because there are 2 boys, and G. Okay, so how they can be arranged? They can be arranged in 3 factorial number of ways, that is 3 into 2, 6 ways. Okay, so what are the 6 ways? 6 ways are, these are the 6 ways in which these 3 persons can be arranged. Okay, so now what happens when we use backtracking? Here this is the initial state. Okay, So at the initial state, suppose the first, we have three options, right? We can pick a girl, we can pick one boy, we can pick the second boy. Okay, suppose first we pick this girl. Okay, so now we reach here. At this point, it is satisfying the constraints. Okay, we are not violating any constraint. The constraint is girl should not be on the middle bench. Okay, this should not be there. So we are picking G first. So G cannot be on the middle bench. So constraint is satisfied. So we go on exploring its children. So the next option can be picking B2. Okay, so we, it means G, then B2. Okay, and then the last option is B1. Okay, so this solution is also satisfying the constraint. Okay, so it means this is a feasible solution. Okay, so now this is a leaf, we have reached the leaf, so we will backtrack to the start. We will backtrack to this state, and from here also we find that there is no unexplored node. So again we backtrack, and when we reach here, we have one more option which is yet to be explored, that is B1, and from B1 we go to B2. Okay, so it means the order is G, B1, B2. So again it is not violating any constraint. Okay, so we will backtrack, backtrack, and backtrack. Okay, now we reach here. Now we pick B2 first. Okay, then from B2, then we can pick G. Okay, now this state is not satisfying the constraints because now G is coming at second place. It means it is violating the constraint. G should not be on the middle bench. It means G should not be on the second place. So this solution is removed from the search space. We do not explore its children anymore, and we backtrack, and then we reach here. Here at the second position we pick B1, then it is okay. So we go to explore its next node, that is G, and the complete solution is feasible. Okay, similarly when we reach here, we backtrack, and we again reach the start state, and from there also we pick the third option which is left, which is B1. Okay, so when we reach here, here we have two options, pick G or B2. When we pick G, this is a known solution, so we backtrack. When we pick B2, then this is okay, and from B2 we pick G, and so this is a feasible solution. And after this we backtrack, and we reach the initial state, and here we found that there are 4 possible solutions to this problem, right? So this is an intuition behind the backtracking algorithms. Okay, so the backtracking algorithms can be used in 3 types of problems. The first is a decision problem, the second is optimization problem, and the third is enumeration problem. Decision problem means you search for a feasible solution, whether the problem has a feasible solution or not, right? In the optimization problem, we search for the best solution. Okay, optimization can be minimization problem or maximization problem. We have seen several examples of these problems. For example, finding the minimum number of coins. Okay, so this was what? This was a optimization problem where we minimized the total number of coins. Okay, and similarly there is also optimization problems which are maximization problems. For example, 01 knapsack. There we try to maximize the profit which can be earned, so that by picking the items in such a way that the profit is maximized, right? And the third is enumeration problem, which we just solved in the previous example, finding all possible ways of arranging 2 boys and girls, 1 girl, right? So here we list all the feasible solutions. That is called an enumeration problem, right?